My name is Elias Yabarow. I'm here with my colleagues, Barquadle and Mohamed. And our project is entitled Arm Charge. Here's an outline of our project throughout the whole year. We started off with the objective of Arm Charge, what exactly it does, the motivations, what we wanted to show. Secondly, we went to the identification of needs and requirements. How could it be useful in the real market as a realistic project? Thirdly, we have a little video introduction of demonstrating this. Fourthly, we went to the design architecture. We'll be talking to you about the level 0, the level 1, and level 2 designs. Furthermore, we're going to dig a little deep into the early prototyping and the testing in terms of comparing Arm Charge with the USB cables and a wall charger. And then we're going to be talking to you all about the task-by-task discussions, the fun spent and the man hours throughout the year, how the load is actually distributed between each member. And then we're going to conclude with the problems encountered and the lessons we've learned. All right, so the fundamental objective of our project was to create a type of device that could use human motion from the arm and actually generate some type of sufficient electricity and use that electricity to either charge your iPhone, your iPad, or in our case, iPhone 4. So here's the identification of need. Many people have iPhones. Any iPhone users out here? No? All right. Battery's not very low, right? All right. So that's one identification of need. Another is that a lot of countries outside the US don't have electricity at all. Some that do don't have very reliable electricity. This product can help people in different countries that don't have reliable electricity give a certain type of electricity that's very reliable for the user. And then another reason is merging exercise with this and mobile needs. So if you're actually doing your nightly jog or your morning jog and you want to be able to actually charge your phone or your battery, you can do so with our product. And lastly, using energy exerted for something productive. If you run from point A to point B, we want to give you the opportunity to actually use that energy in a productive way. All right, so here are a couple pictures of Hurricane Sandy, because this affects people not only in international countries, but also domestically. In Hurricane Sandy, there were 8.5 million people that had no access to power outages. In Virginia alone, you had 270,000 people that had no power outages for several days. We have two pictures here of people in New York City, and they're basically just trying to have some type of outlet for their laptops, phones, etc. So the requirements of our project is pretty fundamental. It should be cost effective, number one. Number two, it should be very lightweight and convenient and user-friendly for the individual using it. Number three, it should generate at least 3 to 6 volts. We're testing on an iPhone mainly, and that iPhone takes about 5 volts output, which is in the range of 3 to 6 volts. It should mimic a wall charger in the sense that you have an AC signal coming into the wall charger, that being rectified with a rectifier circuit, and then fully using that signal to actually charge your device. And lastly, it should give the user options of use in the sense that you have 2 options. If you want to be able to charge your phone, you can go directly and do that, or you can charge it using a battery and store that device. And we have a video introduction of how it works briefly.
This is a 3-minute video, so I guess we'll skip around.
All right, this is a video. You can't really hear it. So here's the basic device right here. All of our circuitry has fit into the pouch that we want to use. Again, it should be very user-friendly and comfortable for the user. We have the fully circuit rectifier circuit fitting into the pouch. And in the second pouch, you have the battery. So if you want to, again, use your battery to use this, you can go ahead and use the cable to connect that. There's your battery. You go ahead and okay, you can stop here if you want. It's kind of blurry, but you have, if you point at the metal brace, which is about 7 inches long, you can show here if you want. This is actually used for stability purposes in the sense that we want to be able to have a strong grip on the motor to the hip. And Khalid is holding the rod that we've been using, aluminum rod, and we've measured the distance from his waist to his elbow. And go ahead and continue. Which is then connected. Go ahead and wait. And there you go. It's kind of difficult. take you to where you're wearing the belt. And there he is wearing the belt. You can stop it if you like. Again, we're using this brace, which is about 7 inches in length, and we drill 2 holes in the middle to actually have the motor go into the side of it. Again, you have a plug-in cap for safety purposes. Attached to this aluminum rod, which is put into the elbow strap. And he just attached the cable wire to his phone. And from there, you're good to go. So you can finish it off. Close everything up. And then you have arm charge, and you're ready to do your job. Now I'll give it to my colleague Khalid, who's going to do more typing.
Well, here's our design architecture. Well, here's the basic design of our device. First, we have the physical work with the generator attached, which is just the arm motion. After then, we have the next part is converting mechanical energy to electricity, which was pretty much what the function of the motor. As the gears turn, it gives us the power, it gives us the voltage that goes into our circuit, and this circuit has the voltage outputs the power into our 2 options, which is storing in the battery when there's no device connected in right away, or storing it instantly to the device. Here's our 2 levels of design. And here's the level 0, which is our black box, which is the black box, which has pretty much just what's going in and what's coming out, which is the only input for our device, the motion, and output is the power going into our device that's being charged. Here's our white box design, which is a little bit more into the black box, but with the components inside. First, we have the motion, which is the rotation of the generator, and that after the rotation of the generator provides us our signal, which goes into our circuit. And then afterwards, the signal we get is rectified with our full-wave rectifier. And then after the rectification, it goes into our voltage regulator. Voltage regulator is there to ensure that we get our desired 5 volts and doesn't exceed it or go below it. And with us, luckily we were getting about 6 to 7 volts, so all we needed to make sure was we didn't exceed our 5 volts. And then after that, the voltage regulator has the option of going into 2 different directions. We had a USB port, as you saw on our device, so the device can be charged instantly. So that connects to the arm, and if the device is not being charged instantly, we have our battery, which connects to the USB device, which is also in the pouch. So there's no wires attaching to the arm. And then our battery can be also be accessed later on to be charged when the person is not in motion. Okay, here's a better look at our circuit. Here's when we generate our signal from our generator, and then it goes right into the full-wave rectifier, always giving us positive voltage regardless of the direction, and then the capacitor, which slows down the discharge as we change direction. And here is our LED to let us know when we have our signals when we're getting voltage. So if we weren't getting voltage or nothing was passing through, to let us know if anything was working. And then here's our regulator, which we use the LM7805 model, which always gives us a constant 5 volts. Over here is the pins for the USB. As you can see, the USB has 4 pins: the voltage bus, and then the data plus, the data minus, and the data plus, and the ground. For charging devices, the data pins are not necessary because that's just for data transfer. But for our device, ideally we are using it for iPhone, and the iPhone requires data pins to get at least 2 volts or 2.8 volts for high current. So we went for giving it a 2.2 volts, which we did by using a common voltage divider, and that's it. Here's the overall design flow. When our device is in idle, we have almost like 2 states, which is idle, when nothing happens, we're just waiting for motion, and then we have the motion, which is the rotation of the generator, all generating our signal, which goes into our circuit, which also is then rectified, and then after the signal is converted to a DC signal, the voltage is regulated. After the regulation, same thing, into the battery or charging device, and the battery can be used in idle state. If it's charged in the idle state, so we can have a device connected to it while the person is stationary. And then prototyping. For our prototyping, we started testing our motor that we got, which was the Kramer's motor 800 model, which gives us 12 volts bidirectionally, depending on direction, 30 volts per minute, and 120 gear ratio. So as the shaft is turned once, all the gears internally turn 120, which is good for the voltage production. And for our prototyping, for our prototype testing, all we did was we tested the capabilities of the motor and see how much force was necessary to create the voltages. Well, the max 12 volts would require a lot of force, and we just went by the regular arm movement. So by gauging the regular arm movement, we're getting 6 to 7 volts. And then I guess that depends on the faster you run. If you run really quickly, you would get more voltage, and then but our voltage regulator solves that problem, so we don't have to worry about it. But also the minimum arm motion was always giving us above 4 volts. And then afterwards, I'll pass on to my colleague Ahmed to tell you guys about how we did our testing.
We did some testing to ensure that we got the required amount of voltage to charge our handheld device. And to charge what we're trying to charge right here is the iPhone 4 right there, and we need 3 to 6 volts to charge the iPhone 5 or the iPhone 4. So what we did was we set up the circuit right, as you can see in the left corner right there, and we measured the voltage at the output using the voltmeter, and we got 4.35 volts, and that fits the range of 3 to 6 volts to charge the iPhone 4. And we also needed to measure the current, which is really important for this project. So we measured the current at the output by setting up the series at the output node and the resistor, and we got 200 milliamps of current. And we did further testing by showing that the iPhone was actually charging. So we set up the circuit right there. We put in a USB universal JST connector, which has a USB pin, and we set it up, connected the phone, and we rotated the generator, and to illustrate that it was charging, we took a picture. We did further testing using the oscilloscope to further analyze the waveform in the circuit. And because we used the voltage regulator and rectification in the circuit, the waveform is always going to be positive, and it's always going to be positive, and it's going to be approximately 5 volts for the 500 milliseconds per division and 100 milliseconds per division. And to further explain the mechanics of the generator, because the generator is attached to an arm, as we're rotating the generator, as we move our arm up, the voltage is going to be it's going to increase. It's going to go up to 5 volts, and as we take it down, there's a moment in time where the hand is not moving. In that instant is when the voltage goes partially down to 3 volts, and as we go back to the negative direction due to the rectification of the voltage regulator, in the negative direction, it's going to be going back to a positive 5 volts, and it's going to keep going like that during this oscillation. We wanted to compare our arm charge device with other like the wall charger and the USB charger. The first step we did was we measured how much the wall charger increases in charge for 10 minutes and increased by 9%. And we also measured how much it takes to fully charge the iPhone, and it took 120 minutes for the wall charger. And we also did that for USB, which took 10 minutes for 5% charge increase, and it took 200 minutes to completely charge the iPhone with USB. Whereas our ARM charge took 4 minutes for 1% charge increase, and therefore took 400 minutes to fully charge the iPhone using the ARM charge. Where the wall charger, comparing the wall charger, the USB charger, and the ARM charge, they all produce voltage of approximately 5 volts for each. But where they differ is the amount of current they produce. The wall charger produces 1 amp, whereas the USB charger produces 500 milliamps, and our ARM charge produces 200 milliamps. Therefore, this illustrates that the wall charger has the highest amount of power, whereas since it has more power, therefore it requires the least amount of time to fully charge the wall charger, whereas the USB requires more time and the ARM charger requires the most of it. To illustrate the accuracy, we used we took a snapshot picture of the time right there. And that illustrates how we did it. 1%. Yeah, to ensure the accuracy right there, we started to oscillate our arm back and forth, but we didn't start the timer until it was 60% for accuracy purposes, because we wanted a whole percent, not a partial percent. So we started the timer at 61%, but we started rotating our arm up and down at 60%. We did outdoor testing where my colleague Khalid ran around Patriot Circle, which is approximately 2.2 miles, and he took 19 minutes and 15 seconds to complete that. And while he was running that across the Patriot Circle, he had the ARM charge attached to his body, and the iPhone increased by 4% battery. Here's a final design: the motor, the rod, the circuit, the battery, and the components, the belt, how you connect everything with this. Task by task. The first task was the motor extension. It was attaching the motor onto our waist and arm so that we can rotate the generator. And the hardware portion also was setting up the circuit, the rectifier circuit, the voltage regulator, and then integrating the components such as connecting the generator to the circuit. And the last task was experimentation, which is pretty much measuring the voltages and current and ensuring that it fitted our specification. Here's a summary of our achievements. We successfully completed the hardware development, the generator extension, the integrated parts and experimentation. Here's financial records. 9 hours worked. It's a total of 240 hours. Problem encountered that.
So a few of the problems we encountered were similar to the team before us. As you can see, one of the problems is turning generated by the individual's arm. Another more serious problem was the reliability of the generator we had. Again, this was due to the fact that we had a small generator that had a 12 volt output, but it had a gear ratio of 120 again. So the fact that for one rotation of the shaft and 120 rotations of the gear inside, that really stripped the teeth of the gears of the generator itself, making it very unreliable and making us actually double the order. We ordered this 2 times. And getting access to the machinery. And the lessons learned, again, are similar to the team before us. Buy everything twice and buy it early, number 1. Number 2, apply all the theory you have now into practice. A lot of theories you learn in class might seem okay when you do a lab in class, but it gets a little more difficult when you actually have to do a project by yourself. So apply that early. And manage your time well, and communicate well between team members, and communicate well when you're actually presenting, because You may know things, but you may not be able to communicate it very well. So that's another important lesson we learned. And we definitely want to take time to thank our faculty advisor, Dr. Gerald Cook, and for his time and his effort throughout the year. Dr. Lori also for giving us a lot of feedback, and Avik, the TA that has helped us a lot throughout the year. And that concludes our presentation. If anyone has any questions.